7.6 trig equations. We're going to solve a bunch of trigonometric equations. I like to start with this flow chart. This flow chart kind of breaks it down into like, what do I do if it's this and what do I do if it's that? All right. So basically, you kind of look at how many variables the equation has, and if there's only one variable, you're going to isolate. This is what we want to do. This is what we want to do because this is the easiest thing to do. And it's not always going to happen like that. If you've got more than one variable, what you would love to do is factor, because that's the easiest thing to do. So if you can factor it, you want to factor it. But the hardest problems, you're not going to be able to factor, and so you're going to have to look for something else. If you can't factor it, then maybe it's quadratic formula, maybe it's some sort of identity, or another trick we can use is to square both sides of the equation, and that's the one that kind of comes out of left field. All right, so that's kind of your basic recipe for how to attack. Let's look at an example. Number one, when I look at this problem, I only see one variable term. You've got sine theta, there's only one theta, there's only one variable here, there's only one variable term, so I'm definitely going to isolate this. All right, if it helps to code switch, do it. Once you figure it out, you won't need to do this. I don't need to do this to recognize what to do, but if you code switch, it's pretty obvious what's going to happen. We're going to need to subtract 1 and divide by 2. So if you can do that in your head, be my guest, do that in your head. You're going to subtract 1, you're going to divide by 2, you get s equals negative 1/2. Now that's not the answer. You can't stop because we're not finding s. Remember s, we did kind of a code switch. S was sine theta. So sine theta equals negative 1/2. We want to solve that, all right? And that's where the chart comes in. Now be careful. Yesterday we talked about inverse trig functions, and we had a chart, and we said inverse sine was defined from negative pi over 2 to positive pi over 2. That's not what we're talking about, okay? Don't even look at that chart today. The only time you'll ever look at that chart is if the problem literally says inverse sine, inverse tangent, whatever, okay? If this is just a sine problem, we're going to do what we've done all semester. We look at that chart, and we know we're in degrees, so we're seeing a 30-degree angle out of that. Okay, don't tell me negative. Don't tell me negative 30. It's a 30-degree angle where sine is negative. All right, and we've done this a lot of times over the course of the semester. We know sine is negative in the third and the fourth quadrant. And you're like, but yeah, yesterday we said inverse sine was only defined in 1 and 4, and there was, well, this is not inverse sine. This is sine. Go back and do what we've done millions of times over the course of the semester. We've got a 30-degree angle where sine is negative. And so I'm looking here, 30 degrees past 180. 180 plus 30 is 210. And 30 degrees before you get all the way around to 360, that's 360 minus 30, is 330. There are two answers to that problem. And there we go. I like that problem. I think that's pretty basic, but you got to be able to get that. One variable, you isolate. Next one is significantly more complicated, all right? If I said how many variables, you might say 1 because there's only theta, but I'm looking at sine theta, I'm looking at tangent theta, I'm really more looking at, there's a sine theta and a tangent theta. It looks like more than one variable to me, okay? I kind of generalized that statement, but there's definitely more than one thing going on, and you're not going to be able to isolate, all right? So again, it might help to code switch if you did this. S times t equals s. Maybe that helps. Doesn't look like I'm going to be able to isolate. So my next thing I would look at is try to factor. Go way back to algebra 1. Algebra 1, you could solve a problem like this. You want a 0, right? So what you did back in algebra 1 is you said, well, we want a 0. So we subtracted that s over, and we get st minus s equals 0. Okay? And I can factor that because I see a GCF. Both of those terms have an s in them. So remember, go way back. Think about GCF problem. I've got an s. I factor that s out. It would be s times t minus 1. equals 0. And we're still thinking about algebra 1. If you had to solve that equation in algebra 1, you use something called the zero product property. Zero product property says that if you multiply two things and get 0, then one or the other has to equal 0. So we went a step further and we said, well, either s equals 0 or t minus 1 equals 0. And so then that t minus 1, I'm going to isolate t. You're going to add the 1 over. You're going to add the 1 over and get t equals 1. It's tempting to stop there, but we're not finished because we haven't done the trig yet. Okay, we did the algebra, that's the algebra, but those are not the answers. We still have to do the trig. So go back and code switch back to trig. Remember, S was representing sine theta. So sine theta equals 0, and t was for tangent theta equals 1. We've got two trig equations that we can solve. Now, if you look at the chart again, you're using the chart, you're going backwards. Sine theta, it's talking about a 0, right? Sine of 0 is 0. But keep in mind, that's a reference, okay? That's a reference angle, and we can't really say it's positive or negative. 0 is neither. Yes, question? You got to speak up. Would it be minus 1? No, because when I isolate this variable, I'm adding 1 to both sides. Where did I get the minus 1? Think about this as multiplication. Okay, s times t is st, and s times minus 1 is minus s. Factoring is like unmultiplying almost. Okay, it's like division kind of. I divided by s, but when you factor, you're trying to write it as a multiplication problem. You want to write it as a multiplication problem so I can use that zero product property. All right. So here we are, sine theta equals 0. We got a 0 degree reference angle. Degrees, yes, degrees. So you got to think about, and sometimes I go back and forth between looking at the picture and looking at the circle, looking at the chart or whatever, but keep in mind, when we find these problems, we're talking about points on the circle, and this specific problem is talking about when the y coordinate is equal to 0. I've got two different places where the y coordinate equals 0. Here's 1, 0, and here's negative 1, 0. I've got a 0 degree angle and 180. 0 and 180. So then we move on to tangent theta equals 1. Tangent theta equals 1, and you look at the chart. Let's look at the chart. That's going to be, right here, right? That's going to be a 45 degree reference angle. 45 is not necessarily the answer. 45 is the reference angle. Since this number is positive, we're looking at where tangent is positive. So I call it a 45 positive. And we know tangent is positive in the first and third. We're going to have two angles. We're going to have a 45 degree angle, and 45 past 180 is 225. Okay. Now, it's very tempting for people. Okay, I want you to watch this because it's very tempting for people to do this. At the beginning of the problem, go way back to the beginning, and they'll say, well, let's just cancel out sine theta. If we divide both sides by sine theta, we'll just get, we'll get tangent theta equals 1. And that's very tempting to do. But if you think about it, if I cancel out one of my variable terms, then I've canceled out half of my answers. And so you can't cancel out one of your variable terms like that, whether it's trig or it's algebra. You can't do that. So I know it's tempting to try to cancel that out, but please don't. And that's exactly what this warning down here says. It says there are 4 solutions in this problem trying to solve the equation by dividing each side by sine theta. would lead to just tangent theta equals 1, that's going to take away some of my answers, all right? So again, notice I code switched in this problem. If you don't need to code switch, then don't, all right? You'll save a bunch of time. You'll save a bunch of space. I wouldn't code switch if I was doing this on my own. I just think it's easier for you to understand probably. But the problem is with the algebra. The hard part that students struggle with is in the algebra and getting, getting the trig by itself. Number 3. When I look at this one, I see 2 different variable terms, okay? Not one. I know I'm not going to be able to isolate this problem. And maybe it's more obvious if you code switch. This says t squared plus t minus 2 equals 0. A lot more obvious now that you're not going to be able to isolate the variable. But we can factor this one. Remember, that was our flow chart. Said if you can't isolate, try to factor. I can factor this one. Factoring, got to remember your algebra. Okay. When I factor this problem, think about doing this type of problem. You're looking for 2 numbers that multiply to -2 and add up to this 1 right there. Got it? Numbers that multiply to -2 and add up to +1. +1 and -2. No, that's backwards, isn't it? That doesn't work. -1 and +2. That'll work. Okay, that'll work. We did this in Algebra 1. You did this in Algebra 1 years ago. Maybe you've forgotten. Okay, the zero product property says that when you multiply 2 things and get 0, that one or the other has to equal 0. So I'm going to skip a step here and say, if this is 0, then t must equal -1. And if this is 0, then t must equal, wait, that's not right. Shoot, go back. I'm struggling up here. T must equal +1. And if this is 0, t must equal -2. Okay? Well, okay. It's not just that it's the opposite. It's because I'm saying this has to equal 0. So we're going to add 1 to the other side. So, it's a little bit more complicated than saying it's just the opposite, especially if there was like a number right there. Okay? If there was a number in the front, it's definitely not just going to be +1. It's going to be +1 divided by 3 because we're trying to solve this and figure out what makes 0. Okay? So, a shortcut, I suppose, is to say it's the opposite of this number, but you got to be careful when there's an extra coefficient. So we've got t plus 2 equals 0. We're going to subtract this 2. We got t equals -2. All right? Now we need to switch back. These are not your answers because we haven't done the trig yet. T stood for tangent x. So we've got these 2 trig equations to solve, and we can look at the chart. We just did this one a second ago, right? When we had that chart, one thing to be careful of is you always have to look at this. That statement at the end there tells me I'm in radians, not degrees. Last problem, it was in degrees. This one's in radians. So when you look at this problem, we're looking at pi over 4, not 45. Okay, this is a pi over 4 where tangent is positive. So pi over 4 where tangent is positive. We know that's in the first and third. Pi over 4, pi over 4. I feel like you should be getting better at this. This one's pi over 4. This one is pi over 4 after pi. Remember, we want to call that a common denominator, so 4 pi over 4. Right after that is 5 pi over 4. Okay. Now, when I try to do tangent x equals -2, you should notice that that's not in the chart. Okay. If it's not in the chart, it's a calculator question. All right. So you're going to need your calculators on this one. Think about how to isolate the variable. That's what we're doing. We're solving this equation. It only has one variable. We're isolating the variable. When we use the chart, we don't really think about it. But when we have to use a calculator, you do. In order to isolate this variable, you got to get rid of a tangent. And how you get rid of a tangent is with an inverse tangent. We're not multiplying. We're not dividing. We're doing an inverse tangent. X is going to equal the inverse tangent of -2. X is going to equal the I got to cancel out the tangent, right? I want X by itself. So on your calculator, make sure you are in radians for this problem. And we just have to do inverse tangent, -2. Be careful. There's a lot of places where you can run into like weird little things. I know the calculator says -1.1, but that's not your answer. That can't be your answer because of this statement right here. It says your number, your answer has to be between 0 and 6.28. 2 pi, 2 times 3.14, 6.28. Your answer has to be between 0 and 6.28. That is definitely not it. Remember, your negative doesn't necessarily mean negative. Your negative is pointing to a location. So maybe we call this a 1.107 where tangent is negative. Let's say 1.107 where tangent is negative. And we know tangent is negative in the second and the fourth. So the numbers are weird and gross and whatever, but it's still the same kind of deal. We know halfway around is pi, so how are we going to find this angle? Right, subtract. We're going to go pi, I just use the pi button, minus 1.107 is 2.035. Remember how we needed a number between 0 and 6.28? That's good, right? 2.035. 2.035. Now we also need to find this angle. And so guess what? 2 pi minus. So let's do 2 pi minus 1.107. 5.176. 5.176. Again, we're looking at a number between 0 and 2 pi, right? 0 and 6.28. Those are your answers. Questions? All right, number 4. These are problems that you technically, I guess, should be able to do. They're kind of like self-check or something like that. But when I look at this problem, 4a, I see one variable I can isolate. I'm going to add the 1 over, so it says sine x equals 1. Sine x equals 1. You look at your chart. We have the chart over here. That's going to be a 90 degree, right? That's going to be a 90 degree angle. In other words, think about where the y-coordinate equals 1. There's only one place where the y-coordinate equals 1. That's 90 degrees. A lot of times there's more than one answer. In this case, there's only one. It's 90 degrees. Part B. I only see one variable term. If I only see one variable term, I can isolate. If it helps you to code switch, think about it this way. If I've got 4c squared minus 3 equals 0, you should be able to tell we're going to add 3 and divide by 4 and then square root. You've done these kind of problems enough where you can probably do some of it in your head. Okay? Add the 3, divide by the 4, square root. Now keep in mind here, when you square root both sides, you've got to do plus or minus. So it's actually plus or minus. Okay? I'm going to get c equals plus or minus square root of 3 over 2. Square root of 4 is 2. Okay? So that's actually two different equations when you switch back, because you're going to have cosine x equals square root of 3 over 2, but you're also going to have cosine x equals negative square root of 3 over 2. don't forget to switch back to your trig. So square root of 3 over 2 for a cosine. That's this one right here. Are we in degrees? 30 degrees? Yeah. This tells me I'm in degrees. So this is a 30 positive, and this is a 30 negative. So really, we're talking about 30 degrees where cosine is either positive or negative. So you're going to have all four, because here's where cosine is positive and here's where cosine is negative. You're going to have all four of those things. So I'm seeing 30 degrees and 150 degrees and 210 degrees and 330 degrees. Why? Because I've got this plus or minus. I've got to see where cosine is equal to positive square root of 3 over 2, and then I got to come back and see where cosine is equal to negative square root of 3 over 2. So the positive answers here and here, that's 30 and that's 330. The negative answers, where cosine is negative, where x coordinates are negative, is over here. This is 180 minus 30 is 150, and this is 180 plus 30 is 210. We've got four answers. The red ones are where cosine is the positive version. The green ones are where the cosine is the negative version. In part C is a little bit harder. If you need a code switch, be my guest. 2c squared plus 3c plus 1. Pretty obvious you're not going to be able to isolate the variable. There's more than one variable term. Can't isolate. Okay? Can't isolate, but we can factor this one. This is a little bit harder to factor. If you want to use quadratic formula, I suppose you could use that instead. It doesn't really matter. Okay? But I know how to factor this one, so maybe we factor this one. Okay? I call this a hard trinomial. That 2 makes a difference there. All right? Now, normally we would say, I need two numbers to multiply to 1 and add up to 3, but you notice they're not going to add up to 3. But that's literally because the way the multiplication works is whatever is over here in this position right here is getting multiplied by this 2. All right? So they don't add up to 3. They only add up to 3 after one of them is multiplied by 2. Okay? Factors into 2c plus 1 and c plus 1. All right? So zero product property, skip this part if you can, says either this equals 0 or this equals 0. I know I'm going to subtract 1 and divide by 2. So I'm going to get c equals negative 1/2. I know over here I'm going to subtract 1. So c equals negative 1. Or look at your trig now. Cosine x equals negative 1/2. Cosine x equals negative 1. Okay. So chart. Cosine, right here, we're looking at 60 degrees right there. Man, that is a 60-degree negative. 60 degrees where cosine is negative. 60 degrees where cosine is negative. 60 before 180 is 120. 60 after 180 is 240. Then I've got to do cosine x equals negative 1. I think when you've got ones and zeros, it's a lot easier to think about the unit circle than it is to think about the chart. We're looking at the point where the x coordinate is negative 1. There's only one. It's at 180 degrees. Okay, this angle right here is 180 degrees. All right, that's a pretty good representation of what you should expect to see on a test and quiz. Those questions are good questions. Good on time? All right. This problem's a lot harder. And I didn't give you a whole lot of room, so make sure you write really small on this one. I look at this one and I see two different variable terms, so I know immediately that I can't isolate. It's also going to be harder to factor because there's no GCF. It doesn't look like the x squared plus something. It doesn't look like one of my factoring ones. So I'm actually not going to be able to factor this one. If you go back to the flow chart, I know I can't isolate. I'm not going to be able to factor. I'm going to try something else. I'm going to try, one of those other two things. Doesn't look like quadratic formula either. Probably going to use an identity or square both sides. Okay. And I know this is weird. This comes completely out of left field, but we're going to square both sides here. Right, small. Okay. So if I code switch, maybe this is going to be easier for you. T plus square root of 3 squared equals S for secant x. So S squared. I'm going to want to square that thing on the left, and a lot of people will mess this up because you can't just distribute the two. That's not how it works. All right. I would hope that you could do this in your head. But when you square something, you can't distribute that 2. You got to multiply it by itself. And when you distribute that out, when you multiply this times this, you get t squared, and this times this, you've got square root of 3 times t, and then there's this one times this one is another square root of 3t, and then this one times this one is square root of 9, that's 3. What I'm looking at over here is t squared plus 2 square root of 3 times t plus 3 equals s squared, okay? But wait a minute. S squared, secant squared, all right? I'm actually going to use an identity. I know I squared both sides, but I'm also going to use an identity because I don't like having two different trig ratios. I don't like having a tangent and a secant. But what I can do, if you look at my board and you look at equation 2b, there's one that we use kind of a lot that says tangent squared theta plus 1 equals secant squared theta. I can use that, and I see a secant squared theta, so I'm just going to substitute in tangent squared plus 1, like that. Okay? And that may not look easy to you at this point, but something super awesome happens right now. Okay? Something really good. We would want to get our like terms together, but you'll notice when you try to subtract this t squared over to the other side, they're going to cancel each other out. T squared minus t squared is gone. And so what I am left with up there in purple and red is an equation with only one variable. We now see an equation with only one variable, and when we only have one variable, we can isolate. This just became much, much simpler because I'm going to isolate the variable. I'm going to subtract this 3, and I get 2 times the square root of 3t equals negative 2. And I'm going to divide by that number in the front. Okay, I know it's messy and gross, but I'm going to divide by 2 radical 3 on both sides. Trying to isolate the variable, right? I'm going to isolate the variable. That cancels out and gives me t by itself. But notice this 2 also cancels out over here. And I get negative 1 over square root of 3, and that should look familiar to you. Okay, that looks familiar. 1 over square root of 3. Think about where we've seen that before. Let's look at the chart again. Normally I don't give you this part of the chart. Normally you have to say, oh, well, if I divide these two, tangent is sine over cosine. If I divide those two, we know those two are going to cancel out. 1 over square root of 3 is pointing me at this pi over 6 right there. Yes?
So if it doesn't say, do you want, like, what would you radians or degrees?
It always has to tell you. And how it tells you if we want radians or degrees is with that statement right there. It has to be radians because 0 to 2 pi is radians. If it wanted degrees, it would say 0 to 360. I suppose if it doesn't say anything, just assume it's radians. But this problem is definitely wanting radians, so definitely pi over 6. Okay? So I guess I forgot to switch back to trig, but that t stood for tangent x. And so tangent x is negative 1 over square root of 3. I know we're talking about a pi over 6 negative. Okay? This is a pi over 6 negative. Okay? Pi over 6 negative. And so we think about this, and we know tangent is negative here and here. And you should be getting kind of good at this. This is 6 pi over 6. So one of my answers looks like it's going to be 5 pi over 6. And then this is 2 pi, so get a common denominator. That's 12 pi over 6. Right before that must be 11 pi over 6. And don't circle it yet because there's one more thing we have to do. Okay, something that you would probably never think to do. Okay, sidebar. Let me change gears completely. Okay, I'm going to give you a very, very simple equation. X equals 4. Right? It's about as simple as I can possibly make it. We can tell that the solution to this equation is 4. Nothing else it could be, right? 4 equals 4. Solution makes a true statement. 4 equals 4. The solution to this equation is 4. All right? Now, if you think about what we did in this problem, the very first step in this problem, we squared both sides. So we're allowed to do that. We're allowed to square both sides. If we did that here, we would get x squared equals 16. And so we've produced a new equation. And this equation, what's the solution? Plus or minus 4. That can't be right. Okay? We've created an extra, okay, something called an extraneous solution, and that happens when you square both sides. We took a problem that only had one solution. The solution was 4. It was very simple. And we convoluted it. We made it more complicated. It helped us solve this problem, but we made it more complicated and came up with an extra solution that's not actually one of the solutions. Okay? So long story short, anytime you square both sides, you're going to have to check. You're going to have to check and see if those things actually work, because I bet you one of them doesn't actually work. All right? Probably the easiest way to check is with a calculator on this one. So go back to the original equation. The original equation said tangent of our number plus the square root of 3. So I type in 5 pi. Ooh, it wasn't 5 pi over 3. It was 5 pi over 6. Shoot. 5 pi over 6 plus the square root of 3. Okay, 1.154 or whatever. On the other side, let's see if it equals secant of that number. Secant of 5 pi over 6. Remember, secant on a calculator, you're going to have to do 1 over cosine. 1 over cosine 5 pi over 6 is not the same thing. That's not the same thing. Left side does not equal the right side, so that's not the same thing. That 5 pi over 6 does not actually work. Okay? Doesn't actually work. Let's try 11 pi over 6. So same deal. Tangent 11 pi over 6 plus the square root of 3. Okay? So then 1 over cosine 11 pi over 6. Same thing, that one works. Okay? One of them works and results in a true statement. One of them does not. This one is not an actual solution, just like negative 4 was not an actual solution. It's extraneous. It looks good. It worked for my new equation that I created, that I manufactured, but it doesn't actually work in the real equation that we started with. This is the one and only solution there. Okay, number 6. When I look at this problem, I only see one variable, so I'm expecting to be able to isolate. You could also do an identity. If you look at the board, it looks like 6A, the half angle identity. But to me, I'm just going to isolate. Okay. Now this one's pretty tricky though, because of this half angle. This half angle makes us do something weird and something different. All right. So I think you probably have seen enough of these to understand if we're going to isolate, we're going to have to divide by this 2 first. I'm looking at sine x over 2 equals 1/2. So far, so good. Here's where people break down, though. You can't get to that 2 yet. That 2 is wrapped inside of a sine function. And so if you're going to isolate a variable, you're going to have to multiply by 2 at the end. That's the last step. First thing I'm going to have to do is get rid of the sine function. Okay? That's an inverse sine if you're looking at a calculator, or if you're looking at your chart. By the way, we're in radians. If you're looking at your chart, where are we at? Right here, pi over 6. This is a pi over 6. Pi over 6 where sine is positive. Pi over 6 where sine is positive means here and here. Pi over 6 and 5 pi over 6. You should be getting better at this. You should be getting better at that. It's pi over 6 before halfway around, before 6 pi over 6. We've got pi over 6 and 5 pi over 6. Now what's tricky is in the past we were done, but we're not done here. Okay, we're not done here because we have not isolated the variable yet. We still have to take care of the 2. Remember, I said that's our last step. In order to isolate, we're going to have to multiply everything by 2. Isolate that variable, we want to multiply by 2 to get x by itself. And so if we do that, 2 cancels this 6, gives me 3. So pi over 3. 2 cancels this 6 in the same way, gives me 3 on the bottom. We've got 5 pi over 3. Now, almost done, but we've got one thing that's really weird about anytime you've got a half angle, double angle, something like that. Okay? When you've got a half angle, and you'll hear me say this a lot, half angle, half the interval. So when we see this 0 to 2 pi over 0 to 2 pi, we're talking about the angle x, okay? And so you have to look at it if x is actually in that interval. Is it actually in between 0 and 2 pi? But what we're going to have to check, which is tricky, is when you look at half the angle, you've got to cut the interval in half and just make sure that checks out, because sometimes it doesn't. Sometimes it does something extra or something weird. And so when I was looking at x over 2, it was right here. I was looking at these angles, pi over 6 and 5 pi over 6. These angles were pi over 6 and 5 pi over 6. And so you have to say, is that in fact in between 0 and pi? In this case, yeah, it's good. Okay? It's good. And if it's good, then everything's all good. And these are your answers. We can circle them. But I'm telling you right now, sometimes that's not going to happen, and it's not always going to work. You're going to have to cross some out. You're going to have to add some extras. Question? 2 pi over, well, it's not reduced. 2 pi over 6 and 10 pi over 6 is right. It's just not reduced. So this is a better answer. Reduce your fractions. I would give that to you, but I know Math Excel wouldn't. Before we get to example 7, I think I need to set it up. So I'm going to show you 2 other smaller, easier examples, I think. Okay. What you need to focus on, I suppose, is this double angle right here complicates some of the issues that we've seen. All right. So before we get there, let's look at a couple of simpler problems. If I do sine 2x equals 1/2. All right, sine 2x equals 1/2. We see that it's a double angle. We're going to have to get rid of the sine, and we're going to have to get rid of the 2. This is an equation with only one variable in it, so I'm going to be able to isolate it. But I can't do the 2 first because it's wrapped inside of a sine. I'm going to have to get rid of the sine first. I'm going to have to do an inverse sine of both sides. And we don't usually think of it as an inverse sine when we look at the chart, but that's what we're doing. If you pulled out your calculator, you're going to get 30. When you do an inverse sine of 1/2, you're going to get 30. Okay, so we've done this kind of thing a whole bunch of times. We see 30, it's a 30 positive because this number is positive. We've done this a million times. We look at where sine is positive and we say, okay, we know sine is positive in these two spots. That's a 30 and a 150. So we're looking at 30 degrees and 150. And in the past, we would have been finished. We circle it, we move on, we're done, okay? But we haven't done anything with this 2. We haven't truly isolated the variable. In the past, we were finished because that was x, but now we haven't isolated the variable yet, okay? And so we're still going to need to do that. We're just going to need to divide by 2. And I think that makes a lot of sense. We're going to divide both sides of the equation by 2, and we're going to get x equals 15. That's not a very good 15. And 75 degrees, okay? But there's one extra thing that we're going to have to do that we never had to do before, all right? I think all that makes perfect sense. Something weird happens when we have a double angle. When we have a double angle, we have to double the interval. And that's kind of hard to understand, but the easy way to remember it is instead of just going around the circle one time, we're going to go around twice, okay? So we're actually going around the circle twice. And so what I mean by that is when we had this 30-degree angle, when we drew that 30-degree angle, we're going to actually go around again and get back to it. So we go all the way around plus 30. 360 plus 30 is 390. We would have an extra angle to look at. Likewise with this one, it was 150. So we're going to go all the way around and back to it. 360 plus 150 is, what is that? 410, 510? 510, I believe. Okay, check me out, all right? All right, so we've gone around twice, and we've got twice as many angles, basically. And so we still would need to divide by 2. So help me out here. What is that? 190, 195 and 255. That is our answer, okay? Something just kind of a subtle little extra step you're going to have to do with a double angle. It's a little bit weird. One way that I kind of check my answer is when I look at like, well, let's just say when I look at this step, when I look at my 2x, my doubled angles have to be in between 0 and 720, okay? But when I go back and I look at x, I have to look at this interval. My x numbers, my x angles have to be in between 0 and 360. That's just kind of a last thing that I would look at just to kind of check. All right, so let's look at the other one. This time I notice it's a tripled angle. It's a tripled angle. And so my practical thing I'm thinking of is I'm going to have to go around 3 times. Okay. I'm still going to do pretty much the same thing. I look at cosine. I look at 1/2. I'm doing an inverse cosine to get 60 degrees. Inverse cosine of 1/2 is 60 degrees. That's a 60 plus. So you look at where cosine is positive. It's here and here. Okay. So I see a 60 and a 300. And in the past, I would have been finished right there. I would circle it and move on. But this time I'm not finished because I haven't done anything with that 3 yet. I haven't truly isolated the variable yet. We know we're going to have to divide by 3. So I'm going to get 20 and 100, but I'm going to save that for my last step. That's going to be my last step. Before I get there, I'm going to go around 3 times. So all I have to do here is take this 60, add 360 on to get back there again, and what is that, 420, I believe? And this was 300. I'm going to add 360 to get back there. That's 660. Okay, so now I've gone around the circle twice, but it's a triple angle. I'm going to go around 3 times. You know, you can say 0 to 1080 if you want. We're tripling the angle, we're tripling the interval, we're going around 3 times. So I just take those red numbers and I add 360 again. 420 plus 360 is, I think, 780. And 660 plus 360 is, what, 1020? Help me out here. Okay. Now, kind of to check, to check, I look at my 6 numbers right here, and I see that those 6 numbers are in between 0 and 1080. So I'm pretty sure I'm on the right track. Just make sure you finish. To isolate this variable, we still have to divide by 3. And you should, I mean, you can recognize that at the beginning of the problem, you're going to have to divide by 3. So we take all of these numbers and divide by 3. I might need a little help here. I'm going to get 20 degrees, 100 degrees. I think that's 140. 220, 780 divided by 3. I don't know what that is. 260 and 1020, 340. Okay. Notice my answers get us back to between 0 and 360. Okay. So now we're ready for number 7. When I see number 7, excuse me, I see this double angle. So I'm expecting to have to do that same kind of thing. All right. But I try my process for solving the equations. We're solving the equations. So number 1, I want to isolate. I'm not going to be able to isolate. There's more than one variable term I'm not going to be able to isolate. Excuse me. This doesn't look like a factoring problem. I'm not going to be able to factor. Okay, go back and look at that flow chart I gave you. Can't isolate, you try to factor. Can't factor, you try maybe quadratic. Can't do quadratic, maybe you do an identity. And that's where I'm going to go with this one. All right. I'm going to go with an identity. I look at this right here, and this looks like some of those identities, the double angle identities. I've got 3 different choices for cosine 2 theta, but I like the one in the middle. I like the one that says 2 cosine squared x minus 1. Okay. This does 2 really useful things for me. Okay, 2 cosine squared x minus 1, bring down the equals cosine x. First thing it does for me is it makes it so that I have cosine x and cosine x. Okay, I've got kind of, I don't want to say like terms, but at least it's not one of them's a double and one of them's a single. Okay, they're both just cosine x's. It's kind of like they're like terms, I suppose. But the thing that really helps me is I don't have that double angle anymore, so I'm not going to have to do that double interval thing. Okay, when I move it down to just x and not 2x, I'm not going to have to do what I did back here when I went around twice or went around 3 times or whatever. I don't have to do that anymore. But I do still have to solve. And so I look at this, and if it helps you to code switch, do it. I wouldn't need to do this, but some of you guys that are a little bit weaker at the algebra, I think this really helps to see what we're going to do. We can't isolate the variable because they're not technically the same. One of them is a square. But what I can do is I can get this over here, and I'm going to be able to factor. 2c squared minus c minus 1 equals 0. And this is factorable, right? This is factorable, and if you're good at factoring, you're going to factor this. I'm going to show you how to do this with the quadratic formula because I don't think we've seen one yet. I want to make sure you've seen it. All right. So if you can factor this, that's what you'd want to do because it's faster. If you're bad at factoring, or if the problem is impossible to factor, you're going to use quadratic formula. So that's what let's do. Negative b plus or minus square root of b squared minus 4ac all over 2a. That's your quadratic formula, right? Maybe you have that memorized. You can always look it up. But I'm going to plug in the coefficients. So negative b, or the opposite of b, remember b over here is negative 1. So I'm going to go the opposite of negative 1. That's 1 plus or minus the square root. B squared, that's negative 1. I always do that one in my head. Negative 1 squared is going to be positive 1. Minus 4 times your A number is this 2 right here. So 2 times your C number, which is this -1 right there, all over 2 times the A number, which was 2. So we get that set up, and then it's just a plug and chug kind of deal. All right. So maybe you can do that thing inside the square root in your head, or, 1 minus 4 times 2 times -1. And do it in your head if you can, or whatever. That's 9. Underneath that radical is a 9. So great, that's going to be a 9 right there. So cleaning up this statement, I've got 1 plus or minus, the square root of 9 is 3, and 2 times 2 is 4. 1 plus or minus 3 over 4. Here's where I talk about branching. I call it branching. You've got 2 branches, and the top branch is when you add. I'm going to do 1 plus 3. That's 4. Don't forget to divide by 4. You get 1. The bottom branch is when you subtract. I've got 1 minus 3. That's -2 over the 4. Reduces -1/2 right there. Okay. Now be careful. Sometimes people will circle that, thinking those are the answers. That was the answer when you were in Algebra 1 class. Okay, we are not in Algebra 1 class anymore. We are in Trig. We haven't done the Trig yet. What we have just found is that C equals 1 and C equals -1/2. It's just like what we would have done if we had factored. Okay, I haven't done the Trig yet. Remember that we code switched to think about the algebra. C stood for cosine x. So we have cosine x equals 1, and we have cosine x equals -1/2. And for whatever reason, people are better at the second one than the first one. Cosine x equals -1/2. We're trying to isolate the variable. We do an inverse cosine, or we look at the chart. What are we going to get? Are we in degrees? No, we're in radians. You got to pay attention to what mode we're in, what language we're speaking. Okay, that 0 to 2 pi tells me we're in radians. So inverse cosine of 1/2, give me pi over 3. We're going to have a pi over 3 where cosine is negative, right? Okay. Now keep in mind, last lesson we talked about inverse trig functions. That's not what this is. Don't even look at the inverse, the domains in the range for inverses. Don't look at that chart. Don't look at the inverse stuff unless it's an inverse problem. This is not an inverse problem. This is what we've been doing all semester long. We did way back in chapter 5. We did it again in chapter 6. Now we're doing it again now. Cosine is negative over here. So we're looking at a pi over 3 in each of these 2 quadrants. And I feel like you should be good enough at this that you can probably do it in your head. I think a lot of you shouldn't even have to draw this. You're just kind of visualizing. We know that halfway around is pi. If you get a common denominator, we call that 3 pi over 3. And so this one is right before that. That must be 2 pi over 3. And this one is right after 3 pi over 3. That must be 4 pi over 3. Okay. Now, cosine x equals 1. You can do an inverse trig, an inverse cosine, and you see that it's 0. It's a 0 degree reference, or 0 radian reference, I guess. It's 0. You really want to think about where it is. I think when we're talking about ones and zeros, it's almost always going to be easier if you think about the unit circle. What this problem says is I want to know where the x coordinate is equal to +1. And so you're like, well, over here, that's where the x coordinate is +1. It's that angle. It is 0. All right, so you've got 3 answers there. 0 and 2 pi over 3 and 4 pi over 3. Okay, now remember, I know we had a double angle, but we didn't have to go around twice because we stepped it down to a regular single angle. So we just did what we've always done. Number 8. I know I can't isolate because there's more than one. Doesn't look like a factoring problem, doesn't look like quadratic formula, probably going to use an identity. All right, so you've got to find an identity that looks kind of like this one. Now there isn't one that looks perfectly like this one because of the 4. So when you look through your formulas, I see sine times cosine, and that's kind of a big deal. That's my indicator. So I'm looking at maybe this one, 7c, sine A, cosine B, or I'm also looking at 5a right there, 2 sine theta, cosine theta, and you have your choice, whichever one you feel like would work better. That's what you're going to do. Okay. So in my opinion, I think what we should do is just change that 4 to a 2 times 2, and it looks a heck of a lot more like one of those identities. That looks like the double angle for sine with a 2 in front of it. Okay. So I know that kind of came out of nowhere. Sometimes you're going to have to be a little bit smart about manipulating your equations. But the double angle sine formula says 2 sine theta cosine theta. So that's what I've got right here. This is sine 2 theta. So I'm using an identity. Don't forget, we've got this 2 in the front. We've got this 2 right here in the front. Equals square root of 3. Okay, now I've used an identity. And now what I'm looking at is an equation with only one variable in it. Okay, that's what I want, right? When I have an equation with only one variable in it, I can isolate. I do that over and over and over again. I can isolate. So I know I'm going to divide by this 2. And I've got sine 2 theta equals square root of 3 over 2. All right. If I'm trying to isolate the variable, I'm going to have to knock out this thing and this thing. I'm going to have to take an inverse sine at some point. I'm going to have to divide by 2 at some point. I can see that right now. Okay. But keep in mind, you can't touch that 2 yet because it's wrapped inside of the sine function. You're going to have to get rid of the sine function first. All right. Notice we do have a double angle. When you do your inverse sine, if you've got a double angle, that's when you're going to have to do this stuff. We're going to have to go around twice. We're going to have to go around twice, and that's okay. We can do that. So when I look at my chart, I'm looking at inverse sine of square root of 3 over 2. Inverse sine, look at your chart. Inverse sine of square root of 3 over 2 gives me, oh, we're in degrees, right? 60 degrees. Okay, you got to pay attention to what language we're speaking. It's 60 degrees where sine is positive. Okay, haven't touched the 2 yet. That's going to be my last step. My last step, I'm going to divide by 2. I've got a sine, okay, positive. I've got a 60 positive. So I'm looking at where sine is positive. I know that's here and here. Okay. I can see my 2 angles. I've got a 60-degree angle in the first. And what's this one? That's 120. Very good. Okay. Now again, if this was chapter 5, we would have circled it. We'd be done. All right. But we're not done because we haven't isolated the variable yet. We're definitely going to have to end this problem with a divide by 2. All right. But what you've got to force yourself to remember is that when this is a double angle problem, we're going to have to double the interval. Okay. Probably easier for you to think about. We're going around twice. Double the interval, we're going around twice. Double the angle, double the interval, we're going around twice. So all that means is this was 60. I want to get back there. I want to add 360. I want to add 360 to this. That's 420. To get this 120, I'm going to add 360 to this one. Add 360, that is 480. And at this point, I've gone around twice. When I've gone around twice, I'm going to stop. Go around twice, you stop. Notice those 4 angles are in between 0 and 720. Okay? But I'm going to divide everything by 2 to isolate my variable. I've got 30 degrees, 60 degrees, 210 degrees, 240 degrees. That's your answer, but you should also notice that that gets us back to numbers in between 0 and 360.